Let us start from where we had left. You see that we had computed how to actually compute that particular problem, which was essentially this one, rather this one, and we did not do it in detail, but we showed you the most important or rather the most useful possibly from a computational point of view, the updating formula due to Broyden, Fletcher, Goldfarb and Channo. The importance of this is that this is positive definite. When Bk is positive definite, Bk plus 1 is positive definite. The problem however is that if you have Bk plus 1 positive definite or Bk positive definite, it is fine in some sense, but the problem is that you again have to compute the inverse when you are actually computing the iteration. So, how do I stop myself from doing this expensive computation of the inverse, because if the matrix is large, then computing the inverse could lead to troubles. So, we can now do something else. We can choose, instead of trying to approximate the Hessian, I try to now approximate the inverse of the Hessian matrix in the Newton scheme with some matrix Hk which is PD. So, usually this is naturally because I want this to be PD. So, basically Hk in some sense is acting as the inverse of Bk. So, in that sense the equation that Hk should satisfy is not Hk or Bk Yk equal to like Bk Yk equal to Sk or Bk Sk equal to Yk, this would satisfy the reverse thing. So, we have Pk Sk is equal to Yk, that is exactly what we had done, right. Now, if B is invertible, I can have Sk, sorry Bk plus, if B is some matrix like this, then B inverse where B is PD, then I have it like this. So, if this is my H, then basically H would be an equation that when H would be a n cross n symmetric PD matrix which will be satisfying H of Yk is equal to Sk. So, in that sense the problem that I really want to solve in order to find H now, if I find H I do not have to invert, is this problem. Of course, it is symmetric, the same story. This is what I need to actually look into. Of course, you can put this as half of this square. What is important at this stage is to understand that here if I take H, then my Newton iteration simply means so even if I do not have much information about twice differentiability of the function, okay, I can assume twice differentiability, it will be always good to assume twice differentiability. I can still do certain operation like this with a positive definite matrix, because again anyway if I put D is equal to minus it is quite simple to note that this is a decent direction, because this is nothing but minus of is strictly less than 0. Now, if I solve this system, what will I get? I will get the following, like the one I got for the Broyden case earlier, the Davidson-Fletcher-Powell case. So, just like the Davidson-Fletcher-Powell update, I will get a similar sort of BFGS update, but now with in terms of age. So, BFGS update. So, if I just do a PD matrix, take a PD matrix, basically when I start with H0 as I and then use this updating formula and use this without even bothering whether the function is twice continuously differentiable, only knowing that it is just continuously differentiable, I can actually get something, some sort of solution by applying this approach. Now, let me look into this carefully. This solution of this under the approach that we had earlier stated would turn out to be so these all consist of a rank 2 update, because here we have a rank 1 matrix plus another rank 1 matrix. So, this is one rank 1 matrix into another rank 1 matrix plus a rank 1 matrix. So, please remember this is a matrix. So, the interesting feature that we again get is the following. If this age is PD, that is positive definite, symmetric for PD, it's symmetric of course, because you have assumed this, that it has to satisfy this, then this is also PD. I will not ask you to prove this, because you can if you wish to prove it, those who are more mathematically inclined, but it is enough for the audience here to really know that okay, this is an update which I can use. And you can compare this with the formula that I have for B, where you see basically here yk has been replaced by sk, right. So, but observe there is not a symmetry in this formula. Symmetry in this formula means what? The formula for H and the formula for B looks quite different, the updating formula. So, people sometimes use a formula called the SR1 method or the symmetric rank 1 method, where the formula for B and the formula for H has a symmetry, they look similar, though y is replaced by yk replaces sk and vice versa. So, the symmetric rank 1 method. So, here we have rank 2 matrices. So, if we come here, so this is a rank 1 matrix, because sk into sk transpose is rank 1 matrix. So, this finally this will be the whole thing would be a rank 1 matrix. So, this is a rank 1 matrix. So, this is a rank 2 matrix at the maximum. So, but here also it is rank 2, but here we will just update it with rank 1 matrix. Now, symmetric rank 1 matrix is rank 1 update is now adding to BK say a rank 1 matrix VV transpose, and that is what I call as BK1 plus 1. But the problem with symmetric rank 1 matrix is that if BK is PD, there is no way I can tell that BK plus 1 is PD, but that drawback is actually covered up by the simplicity of the whole thing and simplicity in the implementation of this thing. And a numerical experience has shown, as Nosedal and Wright, the book which I am using for this lecture partly is for example, this book Nosedal and Wright, Numerical Optimization, which is published by Springer and now available in Indian edition. So, it is a must for those who study optimization. So, you would observe that what he says that numerical experience has told us that it is not a harm to use this SR1 update, and in many cases it is not been PD, sometimes becomes helpful. Now, the problem is that you can ask that if Bk is PD and Bk plus 1 is not PD possibly, then why the method is useful for? How are you going to write down a algorithm with this method? The issue here is the following. The issue is that you write down the algorithm with this method because of the following facts, that nowadays there is a powerful group of techniques called the trust region method, which I believe is not really within the scope of this syllabus, but I will talk about the trust region method as a almost at the last as some sort of special lecture, you can say. So, the important part that I want to discuss here is that once we take the trust region approach, we will show you the trust region approach and we will show you in the use of symmetric rank 1 update in that lecture. So, once we take that trust region approach, then in fact the indefiniteness of Bk1, Bk plus 1 might turn out, in fact turns out to be in its advantage, and that is a very important thing to realize, that even without this I can actually do something if I use this more advanced trust region techniques. So, how do I do the update? That is very important. Here sigma is either minus 1 or plus 1. Right, and then you have to choose this V in such a way that the second equation has to be satisfied. Choose V such that, because that is the major requirement of the trust of the quasi-Newton method. So, you have to choose V in such a way. So, how do I choose that V, right? So, let me now operate this. So, this can be written as, when you take this vector and multiply with the matrix, basically you have so, because this is a vector that you are multiplying. So, you can write this as because I can take V transpose Sk as some sort of associative stuff. In fact, if this is a matrix into Sk, you can show that this is same as V transpose Sk into V. When you have this rank 1 matrix, this is exactly what will happen. So, this is something you figure out from here to here, figure out how it comes by homework. Just take a 2 by 2 matrix and just check it that it is correct and then use the induction. Now, Once you have that, the question would be how do you choose the V? So, my question is okay. Let me choose V as delta times okay. So basically you would have bk plus 1 sk. So bk plus 1 sk here is your yk, right. So yk minus bk sk is sigma times this. So how would you choose V to get something alright? So let us choose it like this, and if I put it back into this equation, then what I will get is so I will leave this to you to figure out. Okay. So, I am plugging this thing in place of V here, obviously bring the bk minus sk to this side. So, once I do that, then what I will have is the following. Let me now choose sigma to be the sign of okay. Now, if I want sigma to be plus 1 or minus 1, basically sign functions are that if it is 0, this is 0, if it is positive, it is plus 1, if it is negative, it is minus 1. But okay, here we will not, we should not take 0 because a thing like this will soon come in the denominator. So, here we will take up this condition that for this time being this is not equal to 0. So, depending on the sign of this inner product, your sigma would be either plus 1 or would be minus 1. Then that would allow us to choose delta as follows, plus or minus 1 by square root of Sk transpose Now, once I have done that, then what I have is the following. I can then put back all those things here. V sigma is plus or minus 1, it depends on, because V on with V you will have the delta. So, delta would have a plus or minus 1. So, if this is positive, sorry, so if this sign is positive, delta is plus 1 or it is minus 1, right. So, if it is negative, this is minus minus plus. So, ultimately here you will always have the plus. Remember, you cannot have, because this could be negative. So, you cannot have a square root of negative number in optimization, because we are dealing with real quantities. So, now if I plug it in, I will get the following result, following update formula for B, SR1 formula for B. So, that would turn out to be more simpler than the others. but keeping its drawbacks. So, this forms a rank 1 matrix, and then I divide by whose okay, of course, sigma has to be in parallel to the sign of this, minus if minus, plus is plus, and so ultimately this will be plus. And because you have taken square, it will come once, because you have delta, delta is that to the power half, because in it will come for both the v's. So, it will become delta square and it will have formula like this. So, now what I want to say is that here, if I look at the formula for H, it would be like this. Okay. So, you see, look at the symmetry, only Bk is replaced by Hk, Yk is change in Yk is replaced by Sk and Bk is replaced by Hk, and everything else remains same. So, that is why it is called the symmetric rank 1 updating formula. Actually, if say Pk Sk is equal to Yk, that implies that Sk transpose Yk minus Bk Sk is equal to 0, then sigma would actually be 0, and the only possible updating would be Bk plus 1 is same as Bk. Now, the problem is, if Yk is not equal to, and then actually you do not have to bother about the sigmas being 0 here. I would say rather you can actually come to this from a very simple approach, because otherwise I can always say that I would like to look at it through sigma equal to 0, but that is not the way people look into that in the literature, because when Yk is not equal to this and still then usually there is, people do not write down any symmetric update formula. See, what happens here is the following: you actually have Bk Sk is equal to Yk, right, and the way Nocedal and Wright approaches it is that I would actually put the sigma equal to 0 and try to get something, but okay, it does not really matter. For me this equal to 0 means the same thing, you do not really update, but they are telling that if this is there, then from the second formula I can say bk plus 1 equal to bk and get a bk plus 1 which is same satisfying the second formula. So, they are telling that this updating is possible from the second formula, and here no updating is possible, no updating is possible. So, this said that this case actually marks the very simple approach we have taken here compared to the other more sophisticated approaches of BFGS and DFP. So, there are obvious reasons that why we go to talk about this, this SR1 formula is that we can provide a simple thing to stop the breakdown of this. You see signum function here, there are a lot of ways one can define it, either you define it at if this is positive, this is 1, if this is negative, this is minus 1, what it is 0, what sign you will take, usually it is given the value 0, but okay, here possibly they want to maintain just the 2 cases and in Ossalin, right. So, we will just follow them and say that okay. You must be asking why this teacher follows a book while he is talking about algorithms, and why does not he follow the book completely when he talks about theory, because the speaker is a optimization theorist and not really an expert in algorithms, though every optimizer knows some algorithms, of course he has to, because this is one of the most important part and parcel of the subject. So, hence in order to give the audience a better viewpoint of the algorithms, it is always better to go to the experts in optimization algorithms who might not likewise be very comfortable when doing advanced optimization theory. Now, I would say for me in both cases the only possible updating would be either bk plus 1 equal to bk or do not update at all. In numerical practice, the updates generated by this SR1 type thing is much better update of the Hessian than BFGS of any other approximation. And the problem is that in quasi-Newton methods, if you want to apply them for the constraint case, then it becomes very difficult to maintain the curvature formula, right. You must have seen the curvature formula at the very beginning, that is if you want the second condition to be true, then necessarily curvature condition has to be true. So, if curvature condition is not true, then the second condition is not true. So, which means the curvature condition really has to be checked at every stage, that okay, the curvature condition is holding. Okay, if the second condition holds, then curvature condition will naturally hold. So, because your bk plus 1 is symmetric positive definite. So, the question is what is this, that in this in constraint cases it is very difficult for curvature conditions to hold. So, if curvature conditions are not holding in the constant case, then there is no other choice if you want to apply quasi Newton to is to take this symmetric rank 1 approach. Now, symmetric rank 1 has a very important property, it is almost like a conjugate gradient property. So, there is a link between the two anyway. Now, if I put the direction of descent as minus hk grad fk grad f xk, then you can write xk plus 1 is equal to xk plus dk, and this dk is now your sk, because this is same as. Now, we consider the use of the quasi Newton method for the case when my function f x is a quadratic function. We had studied them while we were studying conjugate gradient methods. It is same as writing like this, you know, it is just and what would happen if I apply SR1 there? Here my Hessian is always positive definite. So, let me take a starting point x naught. So, take now my question is what happens if I use the SR1 technique to solve this problem. Now, let x naught be an initial starting point. Okay. And then H naught be a starting symmetric matrix. So, as H0 is given to you, so you will go from x0 to x1 by writing x0 to the gradient of that. So, it is A of now, once you come to H0 to go once you get x1, now to get the H1 from where you can again make the thing, you have to use the SR1 update to go from H0 to H1. Let us use the SR1 update. Let us use the SR1 update, right. Now, if that is the case, then now assume, so this is a very important thing, assume that YK transpose SK minus HKYK. So, it is just the thing that you need for the particular HK type updating. This is not equal to 0. We will assume this fact. So, this is a very thing true for all k. Suppose this happens. So, this is a very important step. If n steps are performed, if n steps are performed, then and each search direction search direction dk is xk plus 1 minus xk. Forms a linearly independent set, or I can write and the search directions, the English has to be correct also, and the search directions dk forms a linearly independent set then of course then the interesting result that we have is H of n is nothing but A inverse. So, if H of n is A inverse, then what are we are going to get? Then we are going to get x n plus 1 is equal to x n minus H n A x n plus b. Okay. So, x n plus 1 is equal to x n H n A inverse A x n plus b. So, x n plus 1 minus x n is equal to minus A inverse A x n minus A inverse b. So, that would mean that x n plus 1 minus x n equal to minus x n minus A inverse b, which means that x n plus 1 is equal to minus A inverse b, and thus x n plus 1 is the solution. So, n after n iterations you know what is the solution. So, this is just the solution, because H n becomes A inverse, and you know in general when you have a quadratic function, when you are minimizing over R n and your his n is positive definite, then you have grad of f of x is A x plus b. So, if you want to equate that to 0, then x is nothing but minus A inverse b. So, if x is equal to minus A inverse b, it is definitely the solution, right, because it satisfies grad A x equal to this thing equal to 0, and this will become 0, and of course, because this is a convex function, every critical point is a global minima. So, this is a global minima, and hence x n plus 1 here you see is a solution. So, the question is, how do you prove this fact? So, we will start in our next class by proving this fact, tell you slightly more facts about the rather some sort of convergence of the quasi Newton method, and then go over to the special lecture on linear programming that I promised. Thank you very much.